Morning, everyone. So today we're going to start into our third chapter, which is a unit on acids and bases. It is by far the longest, so as we step our way through, make sure you're keeping up with the review questions, making sure not to leave it too far because the concepts do build on each other fairly quickly. So for starters here, we just want to just introduce what are these things that we refer to as acids and bases. We already sort of have a understanding of them, but we're going to see through today and tomorrow's lesson here, we actually want to be a little bit more specific with the definitions. Sometimes the theory that we know, which is actually referred to as the Arrhenius theory, it's not encapsulating enough here. We actually need a larger theory to actually capture those ones as well. So let's just have a look together here. Starting off here, we have a guy called Lavoisier in the 1700s here. He proposed this notion of a universal acidifying principle, and essentially just spelling that out a little bit here, he said there were some chemicals that demonstrate this property called acidity, and acidity was found. Acidity is the presence of oxygen in compounds. So basically he had figured, well, if I have a bunch of these compounds here, hey, they all behave the same way. Oh, it must be because the oxygen in them that actually causes them to be acidic. If you just think back to chapter 3 from last year, if I take a nonmetal like sulfur, this is sort of the contact process here where if I oxidize the sulfur here, I end up getting a nonmetal oxide. While a nonmetal oxide here is covalently bonded, we know nonmetal oxides typically form acidic solutions. So you can make that note again. Non-metal oxides are acidic, or they form acidic solutions. So if you look at the equations that we saw, we had SO2 upon reacting with water. It's almost like a fancy synthesis reaction. We get sulfurous acid. If I had maybe nitrogen dioxide here reacting with water, we get some combination. These ones here are really common for causing our problems with acid rain, things like that. Basically, our industrial gases, they throw these sulfur oxides and nitrous oxides in the atmosphere. When they interact with rainwater, they end up producing a lot of extra acids in raining down. So that's what Lavoisier sort of made some observations. Oh, these things here that are oxides, they all behave in a very similar fashion. For Arrhenius here, I think a couple decades later, for Arrhenius, he qualified it a little bit. It's actually not so important about the oxygen in the compound. What's actually the characteristic acid particle is actually an H+. So this is probably the definition that we're familiar with. So an Arrhenius acid is defined as a species. It's a chemical. It's a species that dissociates in water, or you can just say in solution, to form or to produce H+ ions. So unlike Lavoisier here, who said, okay, well, acids have to contain oxygen, Arrhenius sort of redefined that a little bit, and he focused more on this H+. Let's just have a look at a typical acid here. Let's say hydrochloric acid. Hydrochloric acid will be known as a strong acid in this chapter. Strong acids go one direction. This one here, upon dropping them in water, water will separate the ionic bond between H+ and Cl, and we're going to end up with H+ and Cl-. The chemical that is able to release the H+, this is called the acid, and we had dropped in water. You can just say in solution, and that's when it separates off H+. I just wanted to have another closer look here at this H+ species here. The H on the periodic table here is element number 1, is 1.01 as a molar mass here. Being hydrogen, we know it has to have 1 proton. The most common isotope here also weighs about 1. The most common isotope is called hydrogen 1. Essentially, is just a single proton. To make sure everything stays neutral, though, if it has 1 positive, it should have 1 negative to counterbalance it. So that's just a hydrogen atom. What happened to the hydrogen atom to become H+? Well, I'm not going to touch the nucleus, or else that might change the element. What I'm going to do is I'm actually just going to remove the electron here. When I remove that electron, you'll notice the hydrogen atom went from being sort of from the center here to the n=1 shell. Suddenly, the size of the radius is a lot tinier. The nucleus is about some 1,000 times smaller in comparison to where the shells themselves are. And H+ is actually just this part. So an H+ is actually synonymous with a proton, right? One of those nuclear particles here. And in fact, what's going to happen here is, especially because we're in solution, we know charges in general are unstable. it doesn't like having this plus charge. Fortunately for us, what else do we have in solution? Well, we have our solvent. So we have water. We saw a little bit of this in chapter 3. Water, in that chapter we had referred to, water can act as a ligand. And what a ligand does is it actually donates an electron pair to stabilize, in this case here, the H+. So what's going to happen here is we're going to get a coordinate bond. We're going to have both electrons here. We're going to form a new covalent bond here and attach to that H+. So this H+ here, which otherwise would have been unstable here, it gets stabilized by this ligand. Most common geometry here is 6. However, this H+ we're talking is so much tinier than even the other ions, like aluminum ions, iron ions, copper ions we've seen before. So what ends up happening is just one water molecule comes around, and we're going to end up with an H+. It essentially complexes with water, and it ends up forming, well, we have 3 H's altogether. Water is a neutral ligand, so water cannot get rid of this plus charge, but what it can do is it can help spread out the charge. Thinking of this plus charge here as a hot potato, instead of just the hydrogen trying to hold onto the hot potato, when it becomes this complex here, when it actually joins together with our ligand, this plus charge is actually sort of spread around the entire molecule. So in this case here, we're going to give this new name. This is going to be called hydronium. So an H+ doesn't exist in solution. H+ is actually a hydronium ion, and a hydronium ion is a H3O+. Another example of polyatomic here, most of the polyatomics up to this point here have been negative ions, but in this case here we actually have a positive ion. So throughout this chapter here, you can see us, for simplicity here, we might just say H+. What's happening to H+ is getting lost here, but it's synonymous with H3O+. So we're going to need ways to actually write equations, either the simplified way, or when it's complex here, we'll call this the sort of complex for water. So that's how Arrhenius had defined an acid here. An acid is something that has an H, so that when you break it off in water here, the H+ ends up getting released. We can also flesh it out as well. For Arrhenius as a base, the characteristic base particle is a hydroxide. So in a very similar fashion here, this is a species that you can say dissociates, or you can just other wording here, species that releases hydroxide ions, OH- ions in solution. So from the Arrhenius definition here, sort of the conclusion we take is, well, if an acid is supposed to get rid of this H's, this one here should be H something. For that something, I usually put an A there, HCl, HBr, H2SO4, H for something, so that upon dropping in water, it's ending up releasing the H. For the base here, because the characteristic molecule is a hydroxide, we would expect it to be something like B with OH, where that B is usually a metal, sodium hydroxide, lithium hydroxide, magnesium hydroxide, okay, something with hydroxide so that water can actually chop that apart. However, we see that examples like ammonia is NH3, it's going to have very similar properties as these base particles. The question here is, how is ammonia supposed to get hydroxide in solution? There's something sort of limited about this Arrhenius definition so far. But that's how we deal with it so far. So as an example for the acid, we are looking at acids having an H and something, sometimes one-way arrow, sometimes an equilibrium, but basically releasing off that H+. For a base, we are going to predict that this one here has something with OH. These ones here, anything with hydroxide here is referred to as a strong base. So this one here will actually be a one-way arrow, and it's going to be whatever your counterbalancing ion is and hydroxide afterwards. So we can just make a note here. The water, which is sort of in the background and stabilizing these charges here, water acts as a ligand. In tomorrow's lesson, we're going to refer to that as a Lewis base. But as it acts as a ligand, it helps to stabilize the charges. Stabilize. Because charges in general are unstable. They're going to really quickly want to pair up, things like that. But in this case here, water, although it's neutral, it helps to spread out that charge there. Let's just recap some general properties we know for acids and bases. So for acids here, there is a common property for an acid that acids typically react with metals to produce hydrogen gas. Right. If you actually look at a little more detail what that reaction entails, we have our acid, which is like HA. I then drop in a metal, of some sort. Let's call it M. And basically the reaction occurs and we end up with M and A, hydrogen gets kicked off. Essentially it's a single replacement. If you check the activity series, hydrogen is fairly low on that chart there. So because the metal is typically going to be more active, the metal here will have no trouble kicking off the hydrogen. We're going to see bubbles forming under solution. So that's just bubbles of hydrogen gas. That would be a nice test for an acid. The bases will not react in the same way. There's other features that we can do. So unfortunately, both of them are actually corrosive, especially when they're really concentrated. So corrosion would not be a good test for, is this an acid, is this a base? We can use a pH meter. A pH meter, pH is just a ruler. Although we're going to do the math of this one here. Usually we divide it at 7. This one here is actually only true at 25 degrees, which we can always assume. The pH 7 here at 25 degrees here is our neutral solution. This is when we're neither acidic nor basic. To become acids, we actually want the number to actually decrease. So 6, 5, 4, 3. We're actually getting to be more acidic. So using the 25 degree as an example here, if the pH is actually less than 7, the lower, farther away from 7 we are, actually the more acidic it is. If the pH is actually greater than 7, this one here is actually going to be basic, right? Again, at 25 degrees. Again, just a tricky wording here. What if I said something like, oh, I'm actually, pH is increasing, right? Yes, I'm going to be looking at the hydrogen. Yes, I'm going to just figure out where I am on this ruler. But in this case, because the acidic is sort of the lower numbers, as my pH number actually increases, pH increases actually means more basic or less acidic. So just watch out for that there. So pH is a nice ruler that allows us to do this here. We can have chemical indicators. So far we've seen like phenolphthalein as an indicator here. Litmus is another common indicator. Sometimes we actually use that in everyday language. Oh, what's the litmus test for this? Basically, it's borrowing that litmus is actually a chemical. Litmus will actually show red color whenever it's acidic, or it's going to show blue in base. Now for litmus paper, itself, the paper itself can be already in the neutral form. It could be like a colorless to begin with. You put it in acid, it changes to red. You put it in base, it changes to blue. Or it may already have the acidified form of litmus here adsorbed onto paper, so it's red litmus paper. If you leave it into acid, it's just going to stay red. If you then put it into a base, it's going to convert to blue, and vice versa for blue litmus paper. We're going to see a section later on studying these indicators here, but at least litmus is an example of one. Some other features of these, although I encourage you not to ingest your chemicals here, acids would tend to taste sour, whereas bases would tend to be bitter. Right? So Coke is actually acidic, but how come it doesn't taste sour? It's because they dissolve so much sugar that it sort of covers over that. But if you just look at the acidity here, it is actually acidic. Vinegar is acidic, so very sour tasting here. Soaps tend to be bases, so they tend to be very bitter. Again, I'm not telling you go taste your soap. In terms of other properties that you might see, for bases here, bases typically they feel slippery. So if you ever spilled a little bit of NaOH on your hand, it's a solution, right? Not only is water, you feel it's very slippery, it's actually the base properties that are actually going to make it even more slippery than that. There is one more common reaction for acids. I'm just going to put it here. So for acids, not only do they, you can make a note to yourself, that was a single replacement reaction. Basically, the metal is going to be more active than the hydrogen. There's another reaction where we can say acids react with not just the metals themselves and release hydrogen, they react with metal carbonates to form CO2 and water. So I make that look a little better. So carbonates. So if you think back to last year, there were some reactions that were just really hard to predict. And that's just a really common property. So let's take calcium carbonate. This happens all the time. Calcium carbonate here is our chalky material. Limestone is actually made of calcium carbonate. This is definitely a carbonate. When we react it with acid, of course you can start off and just be like, oh, it's going to be double replacement. It's going to form CaCl2, right? It's going to be a salt, right? And then we're going to have H and with CO3. CO3 has a 2- charge, H2CO3. So we form this guy here called carbonic acid. The carbonic acid then decomposes later on this one here ends up forming some combination of CO2 and water. So you can skip that carbonic acid step here. It is a general property of acids that if you drop in a carbonate, not only does this carbonic acid just form for a little while, it's going to end up bubbling off as CO2 and water. Right? So those are some common properties. They like asking you questions, well, how do I distinguish an acid and a base? From what I told you, you can do some of these reactions here. You can put on the pH probe. You can test whether it's sour or not. Both of these actually are conductive. So that's not a good test. Conductive. And for conductive, we're looking for having charges that are mobile. The more charges, the more conductive it's going to be. I'm going to list for you some common acids and common bases here. A lot of these ones here you know how to name. So H2SO4, it comes from sulfate. So this one here is sulfuric acid. When you do sulfuric acid, I don't mind F or pH. Either is fine. Sulfuric acid, HClO4, so that's perchloric acid. We have HBr, HCl, HNO3, so nitric acid, and HF. These ones here that I've listed for you are referred to as strong acids. Now, unfortunately, sometimes in everyday kitchen chemistry here, we usually refer to, oh, this orange juice tastes really strong. What we actually mean in that context is it's very concentrated. The taste is very intense. In this case here, we're going to see a section later on. Strong and weak doesn't refer to concentration. I can have a really low molarity solution, 0.001 molar, but chemically speaking, it might still be classified as strong. For strong, it actually just refers to it being 100% ionized, 100% separated. The ionic compound is completely broken apart. So those are just some common acids. Just make sure you know how to name those ones there. We can have H-Chiku, right? This one here is actually an example of organic acid here. The full name here should actually be ethanoic acid, although the common name here you actually have is acetic acid because it's based off of acetate. And acetic acid here, if a very dilute solution of it, is actually what we use for our vinegar solution. Right? For a strong base, surprisingly, strong again means 100%. Surprisingly, the list of strong bases is actually very, very short. The strong bases that we've seen currently are oxide. I'm just going to show you the oxide here. You still have 6 valence electrons. It stole 2 electrons from someone. This oxide is a strong base. It's got a one-way arrow produce hydroxide, our characteristic base molecule. And we have an amine and a negative charge here. Again, it can produce a one-way arrow to form NH3. Those are actually the only strong bases that we have. But what about all the other bases I can think of? Sodium hydroxide, lithium hydroxide, things like that. That's actually cheating a little bit because let's take sodium hydroxide as an example. This one here is an ionic compound. This one here, one-way arrows and breaks up to become Na plus and hydroxide. You'll notice to be strong, I needed it to be a one-way arrow and I need it to form hydroxide. We're going to cheat and we're going to say, all right, anything like sodium hydroxide here, this one here is a soluble, any soluble salt containing hydroxide. Because it's soluble, we learned from our KSP chapter here, it's just a one-way arrow. It's just full dissolving. There's no saturation. In this case here, containing hydroxide is considered a strong base. Right. So it just happened to one-way arrow. That's why we need to be strong, and we need to produce hydroxide to make sure we're a base. Unfortunately here, it doesn't capture all of it. I already mentioned ammonia as an example. The question here is, wait a second, how about ammonia? Like, how does this generate hydroxide? We'll see that in the upcoming lessons. But so far in the Arrhenius definition, ammonia has very similar characteristics with the rest of the bases, but ammonia is definitely known as a weak base. Now you're going to look at this list and be like, wait, I thought you just said ammonia was a strong base. When I'm referring to this here, I'm referring to the left-hand side. The amine, NH2 minus, is a strong base. It happens to create ammonia. If ammonia were then to react with water, it would then weakly, it's going to be in equilibrium, and it ends up generating a few odd hydroxides. Right? So that's just a recap from what you know from before. Some common acids, so hydrochloric acid, this one here is typically our stomach acid. So when we digest the food that we eat in here, it's usually a really concentrated, strong hydrochloric acid solution. Our stomach has a lining of mucus lining around to protect our stomach from the really low pH of the acidity here. When the stomach fluid gets put into our small intestine, it's actually other organs like the pancreas, gallbladder, things like that. They actually throw in buffers, they throw in neutralizing agents so that the acids don't damage our system. In terms of bases here, I would recognize this sodium hydroxide here. Sodium hydroxide is very commonly used for drain cleaner. So sometimes they just say, hey, which of these bases here is used for drain cleaner? Just note down for yourself, sodium hydroxide. Right? Today, sort of a new bit, we're going to be a little bit more broad in terms of our definitions, not just looking at the Arrhenius definition. Let's switch over to something called the Bronsted-Lowry definition. Even this ends up not being complete, so let's start off with the Arrhenius definition here. The Bronsted-Lowry definition, I'm going to put a BL here in honor of Bronsted and Lowry here. Its definition sort of encapsulates all the Arrhenius, but it's a little bit more broad than the Arrhenius definition. So let's see how we're going to modify this one here. A Bronsted-Lowry acid and base. We had already talked about this. The H plus doesn't exist in solution. It can't stay as just one single proton. That's a really, really dense positive charge. It doesn't stay by itself. What's going to happen is it's going to immediately react with water. Water's going to come and complex with it. We had referred to this one here as a hydronium ion, also referred to as a hydrated proton. So an H plus is a proton, but when you react it with water, it complexes and we end up getting H3O plus. Why are there these sort of two theories of acids and bases? Why is it important? Arrhenius theory cannot explain the existence of acids and bases in non-aqueous reactions. So far we've been saying, oh, drop this in water. Does it release H plus acid? Does it release hydroxide? Base. But in this case here, we can have chemicals that they're not actually releasing H plus or hydroxide, but they also have acid and base nature to them. So what we're going to do is we're going to broaden this definition here. You will need to know all, in total there's 3 definitions. We'll do Lewis tomorrow. But in this case here we have, for a Lewis acid, a Bronsted-Lowry acid here actually is very similar to what we did earlier. We're going to say a Bronsted-Lowry acid is a species that donates protons. Now, protons, we already said, oh, it's synonymous with H+. That pretty much here didn't really change anything, right? It's something that is willing to give up an H+. It's the Bronsted-Lowry base that we're going to actually see a little bit different. A Bronsted-Lowry base, although earlier we had said, yeah, bases are supposed to somehow end up releasing hydroxide. That's the Arrhenius theory. For a Bronsted-Lowry theory here, a base is actually just a species that accepts protons. You'll notice in this definition, wait a second, it has nothing to do with hydroxide. Now, for sure, we are going to deal with a lot of aqueous solutions. It is going to somehow generate hydroxide. That's why it's very similar to the bases. But what we're going to see here is we're actually dealing with just catching, receiving the protons, and somehow by doing that, we end up releasing off the hydroxide. So let's take a look at a typical Bronsted-Lowry equilibrium here. For a typical equilibrium, we are only looking at a 1 proton transfer. There's just one H+, almost like a football, that's being passed around. So we're going to start off here. We have HF. That was an acid that I gave you from earlier. This acid is currently holding the football. Acids react with bases, so I'm going to expect the other term is going to be a base. And all that's happening in this reaction is the HF is going to toss its H+, toss that football over to H2O. What happens to the HF? It goes down by an H. Now I'm just left with the F. Because I also lost a positive charge, I now picked up an F- charge. What about the water? The water used to already had 2 H's. It's now going to grab one more H, so now it's going to be H3. It's going to pick up that plus charge, and now it's holding the football, right? So that's all that's happened, right? We have an acid-base reaction there. Now, you'll notice in this equation, oh, this will end up hitting equilibrium. As it ends up hitting equilibrium, how do I go in reverse? Well, all that has to happen is H3O plus just tosses the football back over to the F-. The person that's the donor is the Bronsted-Lowry acid. The person that's the receiver is the F-, is the Bronsted-Lowry base. So, for a typical Bronsted-Lowry equation, we deal with a 1 proton transfer. All you're doing is you're passing this proton around. So, the person that currently has the football, so the HF has the football. Afterwards, it's the water that's holding the football. Whoever's holding the football is the acid. So, in our example here, we have HF. And we have hydronium as the acid. They are currently holding the football. The person that's willing to receive this football here. The water as a base here is going to receive the football, or the fluoride is going to receive the football coming back this way. Those ones there are the bases. So we're just dealing with a one football transfer, right? So we dealt with the reverse reaction. That's why we can identify it there. Sometimes they just list these chemicals and they just say, identify which is acid or which is base. And that's all you need to do, right? So definitely reversible reaction here, one proton transfer. I'm going to indicate to you another common terminology here. And that terminology here is the whole notion of a conjugate pair. So let's do that here. A conjugate pair are two chemicals that only differ, species that differ by one proton. That's what makes it to be a conjugate pair. So a proton, like we said, a proton here is an H+, right? That's synonymous here. Well, my conjugate pairs are, let's say, HF and F- are conjugate pairs. If I'm holding the football, I'm HF. If I've lost the football, I'm now F-. These two are conjugate pairs. You'll notice conjugate pairs are actually on opposite sides of the equation. I have the football on one side, I'm the acid, I toss it, and then when I'm without the football, that's F-. There is another conjugate pair here. Well, water doesn't have the football yet. It's the base. It's in a conjugate pair with hydronium. So H3O+ and water are also a conjugate pair. Those are chemicals that only differ by one proton. And therefore, there's actually two acids and two bases on each side. The conjugate acid is the species that currently has the proton, whereas the conjugate base form, I know each of them have their own partners, the conjugate base here has lost the proton. So when I have labeled my pairs here, the acid is going to be with the proton. So I have HF, that's the conjugate acid of F- without, and then the hydronium is the conjugate acid, and the water is without, right? And you have one of each on both sides. You can't have a situation where both of them are acids. They can't both hold a proton and then both are willing to throw the football, nor can both of them be bases. They're just sitting there and they're like, oh, who's going to pass me a proton? If no one's going to pass it to them, they're never going to react. So you need to be careful of that. In this example, although we would have expected water, oh, water is neutral, water is neither acidic or basic, we see that water actually acts as a base because it ends up receiving the proton from HF. That's what it takes to be a bronze telluric base. So notice water is actually behaving as a base in this scenario. And what they're going to add to this here is they're going to say water can also behave as an acid. So there are other equations. Let's take our ammonium. Earlier with our bronze telluric definition, I couldn't explain why this one here was a base. We'll finally get an example. This time, water actually acts as an acid. The reason why it acts as an acid is because the NH3 wants to act as a base. Again, I need to have one of each. The acid's job is to take the football that it has and pass that one football over to the ammonia. In that case there, we're going to end up with ammonium, NH4+, and look what happens here. When water loses an H, it goes down by an H, goes down by a charge, it ends up forming hydroxide. Yay, we got our hydroxide back. That's what we need to be basic in solution. It's not that the ammonia by itself had to already be holding the hydroxide like sodium hydroxide. In this case, by stealing the proton from water, it's actually the water that actually leaves behind hydroxide. So let's make that note here. Water leaves behind our characteristic base particle here, leaves behind the hydroxide ion, the OH- ion. Right? So therefore, the water has the football, so water is acting as an acid, and the ammonia is acting as a base. Again, we need to have one of each on both sides. The ability for water to do this, where it can be acid or base, we saw a little bit in the last year. Such compounds are said to be, the full name here is amphoteric, or you can use a slight simplification here, amphoteric or amphiprotic. Amphiprotic things will be soluble. We're going to pretty much be in solution, so amphiprotic is perfectly fine. Just as a nice hint for us, how do we recognize which things might be like water that are amphiprotic? Just as a hint, because I still have to be an acid, it will usually have to have an H. Right? I can't release an H+ if I don't currently have a football to begin with. It has an H and usually has a negative charge. So let me just give you an example of this here. Let's take the acid H2S. Okay. Well, no surprise it's an acid because it has an H. This one here is actually a weak acid, so we're going to go through an equilibrium here. It's going to be one proton transfer at a time. So I'm going to ditch the H plus. I go down by an H, go down by a charge. I get HS minus. The HS minus, similarly here, well, I still have an H that has a negative charge. This one here can ditch the other H plus and then be left with S minus 2. Based on my hint here, I've been saying, well, HS minus is probably amphiprotic. This one here currently still has an H. I still have a football that I'm willing to give, but I currently have a negative charge as well. Well, I have an H. If I go forward and I lose that football, I'm acting as an acid. The whole notion, why do I care about having a negative charge here? Well, the reason why I have a negative charge is probably because somewhere along the way I had already given off an H+. That's why my charge actually went down. So what I'm willing to do is I'm willing to pick up that football again and end up reforming H2S. So chemicals that typically have a negative charge and they have an H, those ones there are usually going to be amphiprotic. It's unusual for chemicals, let's say I'm neutral already, H2S, it's unusual for this to yet pick up one more proton and become H3S+. Usually by the time we hit neutral, I already have all the footballs I want, all the H pluses I want, so therefore I don't actually want to pick up a base. As a S minus 2 here, I can't be an acid anymore. I don't have any more footballs to give. There's no other way around it. So, couple key features I just mentioned here. To check if something is amphiprotic, I want you to check. This is just another way of thinking about it. First, check the substance has an easily removable proton, or easily removable H+. Usually if it's ionic compound that has H, it's easily removable. And then the other one that's a little bit tricky here, I want to check whether the species has lone pairs. Because as we're going to see here, if I have a lone pair, let's study that first reaction again. We have a H+ as a proton, and then we have water. Water overall is neutral, right? In this case here, the H+ is actually going to be complex with the water here. This H+ here will be easily removable, and the water species here has a lone pair that's willing to actually pick up this H+. It's willing to do a coordinate bond. Share both of its electrons to actually hold on to any footballs. This football normally would come from another acid, so maybe I have in my solution, maybe I have a bunch of HAs holding hands. When they actually break up, they separate to become H+ and A-, and basically water is willing to pick up the proton, so water can act as a base from this HA here. Right? Some other terminology here for acids and bases, especially for acids here, they can be monoprotic. Monoprotic mean they only have one proton, so like HA. Diprotic, like the H2S here, have 2 protons. And triprotic, you get the idea. This one here is 3 protons. It just depends on how many footballs it's willing to give. We can say in general, these ones here are called polyprotic because they have more than one H+ that they're willing to give, but it's only going to be one at a time. Now, with any good rule, there's always exceptions. So there's 2 exceptions I want you to track here. For an organic molecule here, we'll see a functional group called a carboxylic acid. These ones here all end in ku. So if you remember our CHQ here, if I drew this out, we're going to do this on the organic chapter a little bit more afterwards. At first, you may be like, wait, acetic acid here has an OH. Wouldn't that be a base? Totally true. This one here could have been a hydroxide, but it's not just holding on to the OH that makes you a base. You actually have to be able to release this OH. In this case here, turns out the C and O is a strong covalent bond. When water comes in, it can't snap that bond and separate off hydroxide. It can only snap this bond here. So what are we left with here? We have the other H's are still fine, C11O and O. The reason why that O and H bond breaks, what we're going to end up seeing is we end up getting acetate. We're going to end up having a resonance structure between these two here. Having resonance adds stability. That double bond here is evenly shared between the two sides overall with a negative charge, so therefore this H+ is referred to as easily removable. It's easy to break off that H+. So you're willing to give up an H+, you're acidic, although this one here is in equilibrium. For organic base, again, another functional group just you want to recognize here. NH2- we had seen on the backside, that's referred to as a strong base. NH3 is actually a weak base, but both of them have a lone pair. This is sort of breaks my rule here. Usually things like grabbing protons until they're neutral. So sure, if I had, let's say, methylamine here. So CH3, It's that amine functionality. We are currently neutral, right? There's no reason for you to pick up a proton, and yet here's that part you need to be careful. You might actually have a lone pair. If you have a lone pair and you have the odd H plus just sitting around somewhere, it's actually the lone pair that can actually grab the H plus, and they can actually react. Again, a weak reaction, so it's going to be equilibrium. We're going to still have CH3 NH, but this time we're going to have 3 H's and an overall positive charge, probably the only time we're going to have a positive acid. And in that case there, pretty much we're going to still have the original molecule, and I would have coordinate bonded with an H plus, so that overall my species here is actually positive. So because I was willing to receive an H plus, that automatically makes you a base. Okay, so try out your questions for a little bit here and we'll go from there. Thanks guys.